So I want to go through something for the TI users. I want to take this data set of 36, 6, 30, 33, and 30, and I want us to go ahead and find things like the mean, median, mode, and the mid-range. But then I also want to find something called the range, which tells me how this data spreads out. So the mean would be if we add these up. Okay, we get 36, I'll do this by hand, 36, 42, 72, 75, 115, 144, 1, 2, 3, 4. So we get that again, 42, 72, 105, 135, divided by 5. Okay, that's going to get me 27. I want to find the median, so I got to put an order, 6, then a couple 30s, and then a 33, and a 36, and 1, 2, 3, 4, 5. The middle spot is n plus 1 over 2, 5 plus 1 over 2, 6 over 2, which would be the third spot. So that's why the 30 is the median. What happens the most frequently? Also 30, which happens up there twice. And the mid-range would be when we average the extremes. We would take this value of 6 and 36 and average them together. So then we'll get 42 over 2 for 21. And all those are trying to find where the middle of the data is, or at least something about the frequency of the occurring of the data, or something like that. So what's it trying to do is help us locate middle of the data for something that we would commonly call the average. Now the range gets into the concept of dispersion. It wants to know how far apart the largest and the smallest are. So the range is going to actually equal the maximum minus the minimum. We could say specifically that the range goes from 6 to 36, but if we want one number, we'll take 36 minus 6 and get 30. But there's another way to say how this is dispersed. This could be a range of 30 centered at 21, so then we can up goes 15 up and 15 down and gets us from 6 to 36. And that's, if you only have a little bit of information, what you can do to start to think about where is it centered and how spread is it. But we're looking here at dispersion, which dispersion measures spread. And I'm going to write a couple numbers down that we get from a TI 80 type calculator, where we put the data in as a data set. And to take you through that again, what we do is turn this on and we go to statistics, and we want to edit some data lists, so we go to option 1, edit, and pick a list that we want to work with. I might just go right ahead and clear my list number 1. So I'll go up to the name of number 1 and hit clear. If I don't want that anymore, I can use a different list also. But I'm going to go 36, enter 6, enter 30, enter 33, enter 30, and I have my 5 values. It's looking for me to enter the 6th. Now I will do some statistical calculations. So I'll click the statistics button at stat, and instead of editing it, I want to calculate here. So I'll hit the second or middle button, and it says calculate number 1 single variable stats. That's perfect for me. I'm going to hit 1. I do want list 1, so I'm going to make sure that I'm pointing at list 1. I don't want a frequency list. I'm not mixing it up with some other thing to do weighting, and I'm ready to do some calculating. And I do come out of here with a mean of 27, X bar. I get the value of 135 for the sum. It gets for me, the value of S of X is said to be 12, and N is 5, and the minimum is 6, and the median is 30, and the max is 36. But there are these things that show up there that don't have any meaning to us right now, and that's S of X equals 12, and this thing that looks like whistle X, it's called row of X, and that one is listed as 10.733 will be enough to get me started, so approximately 10.733. And those are also measures of spread. What they're trying to do is tell me how spread out is the data, and what they'd like to do is figure out some way on average how far are numbers from the mean. And so what they'd like to do is another measure besides range, describing dispersion. And range is not enough all the time. We can find something called the standard deviation. Standard tries to make it for everyone represented, and deviation is how it varies from what we think is the average. What this is going to do is it's going to measure deviation from the mean, and these are two values of dispersion that we'll keep here. There's our data set, and this is what we would call a sample standard deviation, and this is what we call a population standard deviation. And with the population, you're going to use n, and with the sample, you're going to use n minus 1. Now, the difference between a sample and a population is a population must include everyone. A sample tries to get a group of people that's smaller than the whole population to represent what's going on in the population. So sampling uses smaller groups and tries to make judgments about the whole thing, the whole population. So a census would go out and take on the entire population, but if we are just doing an experiment, we might do a sample of some of the people in there. And so we get two different outcomes for the standard deviation based on whether we're looking at everyone that we know to exist or looking at a portion of the population. And I just wrote here right now, use n minus 1 for the sample and use n when we're doing the population. And let's look at what the standard deviation tries to do. The standard deviation looks to represent, so I'll say represents, variation from the mean. Because it's standard, it tries to incorporate every data value that we have and see what do they come out overall when we group them together and look at the big picture. How much do they tend to move away from the mean based on the standard deviation? So, there's a process for finding this. And what happens is variation can lead us to almost the same word, to variance. And variance leads us to the standard deviation. Variance is a mathematical calculation. Variation is an ongoing phenomenon, that things are not all exactly the same, so there's variation among the items. Variance is a mathematical calculation that we're going to make, and it's not good on its own to just get the job done until we can get it standardized and back to the scale of what we're actually measuring in the first place. So here's how we go ahead to find the standard deviation. Of a data set. And we can do a small data set and we can do it by hand. Number one, you would find the mean. Number two, find the difference between the mean and each data value. So you do it for each value. So with lots of values, you're going to have a lot of contributors to this. Now the difference can be higher than, you can be higher than the mean or you can be lower than the mean, but we would have found out already through work we've done previously, such as in the DICE lab that counted as a quiz, that if you take the variation from the mean from all the values and you add them all up, they make 0, because just as many times as you go a little bit or a big amount above, just as much weight comes with how far you are below the mean, so that they wind up back in the middle. And therefore you can't just add up the differences when some are positive and some are negative, and you'll get 0 every time. So you're going to square each difference, whether it's positive or negative. But now it's become squared, so it's out of scale with the numbers we're actually measuring. Add these up, and you'll get what we call the sum of squares. And now you have all of them contributing. Now what the deal is, especially if you have a small size sample or population, what we're going to do is if you have a sample, you're going to divide by n minus 1, which is less than n, and therefore you're going to divide by a slightly smaller number, and it gets you a bigger outcome. We're going to find that here, than if you divide by n. For example, on this one, n was 5, but n minus 1 would be 4. And so let's see what we get. We're going to add up the sum of squares, and we're going to divide by n minus 1. I'm going to put n minus 1 in parentheses because we're doing a sample, or n for a population. But we're going to stick with the sample. We're going to go for the sample standard deviation. And one of the things that I have found is that if you only have 1, you try to divide by n minus 1, you're going to divide by 0. It will not let you do a standard deviation if you have only one value. It'll try to divide by 0 and blow up. And the other thing that happens as n increases, then the difference between n and n minus 1 when you divide by it becomes less and less significant. So the bigger sample you can get, the more you can rely on your data. But this is what we're doing. It has something to do with what we call degrees of freedom. And I actually read about this in the statistics book we used to use in the statistics course here at Norwalk, and it said n minus 1 is based on something called degrees of freedom, which is beyond the scope of this text. And that's a college statistics textbook. We're not even at that level. We're doing a survey of what's going on. So we're going to go with n minus 1 and just know that n minus 1 is going to reflect a better value of what's going on with how far we are from our values than if we divide by n. So we're going with n minus 1. It's one of the rare things where I'll say a little bit of faith, please, for what we need to get done in this course. Number 6. Take the square root of this sum. Take the square root of this value, because everything was squared earlier. We got to scale it back down to the size of what we were initially measuring. Squaring them up made them all squares, and so they may get bigger or smaller, depending, mostly bigger. Add these up to get a sum with contributions from ones that are too high or too low. Because we added them as squares, everything contributes unless it's a perfect fit, then it contributes to 0. I did read that there was, back in college I read there was an option when they were making this up to say we could have just taken the absolute value of the difference that is created, so it wouldn't make 0, everyone would have their contributions if they didn't equal the mean. But we went with the squaring and unsquaring, because then you don't have to know whether to reverse the value because it's known to be negative, or just work with it. If you square it, it'll take care of all the negatives out of your work and get you back to where you want for your sum. So we take the square root of this value, which brings us back into the scale of what we want. Now what happens is when we divide by n minus 1, we get the variance comes from here. And that's a number based on how much variation it is, but a single number, but the number's made up of all these squared values that got added together so they all contribute. If we want to bring them back down to the scale that we truly need, this will get us our standard deviation. So what I'd like to do here is go through and let me just see. I'll turn this back on. It should bring it back to me. Yeah. Okay. I want to get the standard deviation of what's going on here with that data set. So what we want to do is remember that we've already found the mean, right, for that value, set to be, I forgot what it was, but maybe you remember, 27. So let's try and get the standard deviation out of this. So I'll leave the rules down there for us, and hopefully it'll fit on this spot. I'll also leave that. But what we get is a contribution from each one of the values based on how far it is from being equal to the mean. We square it to make sure it has a positive or 0 contribution, and then we combine them through adding. Then we divide back down for scale, and then we unsquare them to get them scaled to the units and size of what we're looking for. So if we have 6 and 30 and 30 and 33 and 36, it doesn't matter what order we use them in, but we subtract 27, we'll see that this one gets me negative 21, this one gets me 3, 3, 6, and 9. If you add 3 and 3 for 6 and 6 is 12 and 9 is 21 plus negative 21, it will zero out. However, if we square them, negative 21 squared, 441, 3 squared is 9, 3 squared is 9, 6 squared is 36, and 9 squared is 81. We'll add those up. Okay, 441, 450, 459, 465, 495, 496, 576. That's the sum of squares. And there's another formula for finding the standard deviation using things in a slightly different way. We're not going to go into that either. But now we've got our sum of squares. So we found the mean. We find the difference between the mean and each. We square each difference. They show up on their line. We add them together. We got 576. Let's divide by n minus 1. N equals 5. N minus 1 equals 4. So we take our 576 and we divide it by 4. And we get, well, let's see, it's 600. It's going to be 6 light of being 150. I think we get 144. Okay. So that is our variance. Now, this doesn't find the variance for you because it figures if I give you the standard deviation, you can hit a button or two and get it squared out here. So now we're going to take the standard deviation. We're doing it dividing by n minus 1, dividing by the 4, and so this will be for the sample. And we're going to take the square root of 144. Nice. 12. 12, sample standard deviation. Now, if you want the standard deviation for the whole population, we have an option to use n instead. And we could go with n is 5. And if you go with our value of 576 divided by 5, okay, we will get an exact terminating decimal for this. 576 divided by 5. Get 115.2. This is the population. Not the one we're interested in, but what would happen with that is if we take 115.2 and then we want to take the square root of that, we'll see the 10.733. And so what happens is the calculator does go ahead and find for you the population as well as the sample standard deviation. The one we're concerned with is not the population. We're going for the sample standard deviation. Let me go through this process. Now, how can you get the standard deviation using this? Well, you put the data set in as I did, and then you run the statistics as a single variable statistic. And then you go ahead and look up where the S of X is for your standard deviation. And the S of X came up here if I go back to stat and I ask it again to calculate for me the single variable statistics on list 1 with no other one. It's going to get me S sub X is 12, standard deviation of 12. How do I get the variance from that? I take the 12 and I square it. So if I take the 12 and I type it in, I power it up to 2. If anyone ever needs the variance for some reason, which to me is less useful than the standard deviation since it's not in the right scale. But if you do need it, you can square to get it. They give you what's most useful with an easy step to get a precursor to it. And so we've come up with that. So what this means is that on average, based on the derivation of the standard deviation, how much does a value tend to miss hitting the mean of 27? And this says that 27 is the mean, and we want 12 to be our standard deviations, which would be kind of these standard steps that we take to find values in our data. And now, I want to give you two data sets, and I want to find the standard deviations, very short data sets, but I want to go ahead and find the standard deviations and see what it means for these values to get them. So first we'll do one, and we're going to go through the process of finding its standard deviation and see what it comes up with. Then we're going to plot the two values, the values of each set on the same graph, and look at the difference of what it means when there's a greater variation, greater variance, and therefore a greater standard deviation. First data set. Set A will be 6, 11, and 13. 6, 11, and 13. The mean equals 10. Because you get 6 and 11 for 17, and 13 makes 30, divided by 3 is 10. So they have the same mean, and they have three values, and they have the same median, 11. Because I'm going to put the other one over here. But this one is negative, is 2, 11, and 17. Now if you add those up, you also get 30, divided by 3, and the mean will get you 30. The median will also be 11. So these look like, hey, they're the same, based on where the middle is. Well, what does standard deviation tell us about these things? Well, let's go ahead and find out. All right. Since the mean is 10, the difference is, okay, if we go 6 minus 10, this is 4 below. 11 minus 10 is 1 above, and 13 minus 10 is 3 above. Those add up to 0, but then the squares, okay, 16, 1, and 9. Sum of squares will create for you 16, 17, 26. So now if we go for the standard deviation, if we go for the variance, we take our 26 and divide by n equals 3. We'll divide by n minus 1 is 2. We'll divide by 2, we'll get 13. Let's go to the other one. Think about our differences. The mean was 10. 2 minus 10, negative 8. 11 minus 10, 1. 17 minus 10, 7. Squares. 64, 1, 49. So if we add these up, that's 50 and 64, sum of squares is going to get me 114. N equals 3, n minus 1 equals 2, so the variance, 114 over 2 is 57. Let's find the standard deviation to 2 decimal places. So we'll take 13, which gives me some indication of how much it varies, and let's bring it down to the scale of what we're actually measuring. So we'll square root it. Get 3.605, or approximately 3.61. Or even we'll go with let's go to 1 decimal place. That'll make it a little easier to get. We got 3.60, will bring us to 3.6. Now, let's go to the other one. So we'll take the square root of 57. It's going to be over 7. 57, how do I know that? Because 7 times 7 will get me to 49, 8 times 8 will get me to 64. This will be 7 something. And it does turn out to be 7.54, which will go with 7.5. So the middle value, if we consider it the mean, is 10, and it figures on average these are missing 10 by about 3.6. The middle value on this is 10 for its mean, and it's missing on average by about 7.5. That's what it's saying. So what I'd like to do is create a graph of these on a number line situation. I would like to go from 2 to 17. Maybe we'll go up to 20. We'll have 0 here, and then we'll have 20. way we'll have 10, and half between those will go 5, and half between those will be 15. Now let's put the blue ones on the graph, okay? Blue we have 6, and 11, and 13. Red, we have 2, and 11, and 17. Each is thought to be centered on the 10. We'll look at the closeness of the blue dots to the green line compared to the closeness that the red dots have to it. And that's a definition of the spread of what's going on here. Now what I'd like to do is go out as many as 3 steps on here and see where they go. Now let's call a step a standard step. We'll do the blue one first. What we're supposed to do is go 3.6 every time we take a standard step. So we'll go to 13.6 about here. And another 3.6 will take us out to about 18.2. And if there were a third one, we would put another, 17.2, sorry. And another 3.6 will go to 20.8. And now we can drop by 3.6 each time, which get me down to 6.4. And another 3.6, which will get me down to 2.8. And another 3.6 will take me to negative 0.4. And so we have 3 standard steps of what's going on with the blue. Red, however, has a bigger spread. Red has a spread of 7.5, so red is going to have its first one at like 17.5. Okay. 25. 32.5. Now this one will go to 2.5. Negative 5. The other one's off board. We're on center. It's out here, I'm not writing on the wall. But there's something thought to be important about 3 standard deviations. Very important stuff happening with 2 standard deviations, because standard deviations are driven by what your data set tells them as to how far is an average step of being away from the mean. So that concept of standard deviation is going to be much more useful when we get into applying the standard deviation to the normal curve, which is coming up in the next lesson. What I want to do now is give you a couple of standard deviation rules of thumb. These are rules that you don't need to go and apply all the numbers and crank out all of what they have to say. But what we'd like to do is look at the 2 standard deviation rules of thumb. So I'll take this stuff down and give you these 2 rules that'll lead into the next lesson that we're going to have. 2 rules of thumb regarding standard deviation. And they are A, nearly every data value will lie within 2 standard deviations of the mean. In fact, we can say to some degree that if you lie more than 2 standard deviations above or below the mean, you might be classified in a lot of circles as an outlier, or close to it, depending on how far out you are. The standard deviation is approximately equal to the range divided by 4. Because the standard deviation, you get 2 standard deviations before you cover almost all your values in each direction. We have 2 up and 2 down. That is 4 bands, 4 steps. If you then take the range, which has your outliers included, but if you don't have outliers, then even more accurately, take the range and divide it by 4. You're saying, here's the spread of my data, and let's find 4 steps that cut that up evenly, and that'll give me a really good approximation of the range. So let's find the approximate standard deviation. This is the approximate standard deviation is equal to. So on this one where we found the range of this was 13 minus 6, it'll get you 13 minus 6 over 4, 7 over 4, get you 1.75. Very small data set, so it's hard to have a rough estimate be very accurate, but it gets you 1.75 as a number to work with. And over here, let's see, this was our standard deviation. Now, we got our approximate standard deviation. Let's take the value that goes from 17 minus 2 over 4. That's going to get you 15 over 4. It'll get you 3.75. Now, it's not really close to what we came up with when we did our computation, but we definitely see this one having smaller steps and being closer into its mean than the red one. And that's how we can compare the width of the steps taking you through the spread of your data. And that's what the standard deviation tries to do. It tries to locate some number that's going to tell you, okay, if I'm allowed to take 2 steps up and 2 steps down, I want to cover almost all my data, get me a number that'll do that. The accurate one done through computation, we did it with really small data sets here, will come up with your standard deviation. But if you only want to know, if all you know is the big and small, right, you don't want to do a lot of computation, you can take the range, cut it into quarters, and you'll find the standard deviation that'll work for you that way as well. So those are the 2 things that lead into our beginning to understand what the standard deviation does. We're going to play that more heavily in lecture 11. So that's what we have.